So now we're going to get into the different so now we're going to get into the different types of triangles. So this first type of triangle is isosceles, and they have the characteristic that two of their sides are equal. And if two of their sides are equal, it's kind of forced that actually two of their angles must be equal as well. Probably have to get into a little bit of trigonometry to prove that, but that is a fact. Typically, people talk about isosceles as two equal sides, but they will also have two equal angles. Now, equilateral is that all the sides are equal. And again, there's a property about the actual angles of the triangle, and that's that each of them are 60 degrees. And then the last mentioned triangle on the slide is scalene, and it doesn't really get talked about that much because it doesn't really have a whole lot of cool properties. So scalene triangle has no necessarily equal angles, no equal sides, and so we can't use a lot of the cool tools that we have in mathematics to do a whole lot with it. So the Pythagorean theorem is kind of one of those theorems that if it's not in the top 5, it's certainly up there of theorems people have memorized. Maybe less so people actually understand what it's about and what it's used for. And it's used to find different sides of a right triangle. So a right triangle is a triangle that has a 90-degree angle, usually represented with that box kind of in the bottom left of the triangle. And so what it tells us is that of the 3 sides, a squared plus b squared is going to equal the longest side, c squared, and c, we call that the hypotenuse. So as an example, we have a 15-foot ladder and it's placed against a wall of 9 feet. From the base of the wall, how far up the wall does the ladder go? And this is kind of a classic example of Pythagorean theorem, because we can usually, if we're finding the height of something using a ladder or something like that, is we can trace the distance from the bottom of the object out to the edge of the ladder, where it's kind of hard to measure from the ground up. And so that's kind of something classic that we see when we're dealing with triangles. And so to do this, we're just going to use Pythagorean theorem and kind of fill in the blanks. So I have a 15-foot ladder, and you can kind of picture it with the blue triangle. The ladder is going to have to be that hypotenuse, that longest side. And then the truth of the matter is, it really doesn't matter whether or not it's A or B at that point. But I believe I made a 9 inches. Yeah, 9 feet, 9 feet. So I put in 9 feet for my A, 15 for my C, and then I just do some simplification. I square by 9, I square by 15, subtract 81 from both sides, take the square root, and I get 12. Now, you might remember from earlier in the class when we dealt with square roots, anytime you square root both sides, you need to do plus or minus. That's not the case here because we're dealing with distance, so you wouldn't really say that the height of the ladder is negative 12 feet up from the wall. That doesn't really make sense. So that's why we're only really dealing with the positive. And something that's worth mentioning is I actually wouldn't get full credit for the answer that I have up here. I need to include my units. So it should be 12 feet. Oh, perfect. 12 feet up from the base of the wall. Moving on, area of a triangle. And the nice thing about this is with Pythagorean theorem, you have to have a right triangle. With this formula, you could do it with a scalene triangle. It doesn't necessarily have to have any property other than the height has to make a right angle with the base. And so that's how you determine your height, is you go form a right angle from your base and you trace it up to the tallest part of your triangle or that vertex. And then you just do 1/2 your base times your height. Or if you want to kind of just deal with the letters, it's b times h divided by 2. I don't really see that often, but I've had students that prefer that formula. They're the same thing, so I'm fine with either one. I'll probably talk through examples as the first formula though. So I have a basic triangle here. It's 3 feet it's 3 feet, has a height of 3 feet and a base of 8 feet. So then I do 1/2 my base times my height. And so 8 times 3 is 24, divided by 2 gets me 12. And since I'm dealing with area is always going to be that units squared. So that's where that feet squared comes from. Now with this triangle, this is one that seems like we shouldn't really be using the 5 inches because that 5 inches isn't inside our triangle. So quite often people think, okay, that can't be the height. That's not true. Again, it's what forms a 90-degree angle with my base. So sometimes if I have weirdly shaped triangles, that height might even appear outside of the triangle. But in this case, it really isn't that much more work. I just, again, do 16 times 5 divided by 2, or 1/2 16 times 5, and I get 40 square inches. Now for this guy. So this happens a lot in mathematics. We kind of see a trend and we say, oh, okay, I get it. I have two numbers, I'll multiply, divide by 2, and I'm good to go. We have to be careful because here, my height is 7 meters. That's absolutely correct. But my base is not 25. And sure, you might argue, okay, well, I rotate it so that 25 is the base. I can spin my shape so that the 25 is on the bottom of the screen. But that still doesn't work because that's not, then my 7 would no longer be my height. It would be off at a weird angle or something like that. So instead, what we're going to have to do is we're going to kind of combine concepts. We're going to use the Pythagorean theorem to first find the height. And then once we have that, or I guess the base in this case, the base, and then once we have that, then we can use our area formulas. So I'm going to say my A is 7, my C is 25, and same process that we saw in the last slide. I'm going to square my 7. I'm going to square my 25, subtract 49 over, take the square root, my B is 24. So that's the height of my triangle, or the base of my triangle. And now I just do 24 times 7 and divide it by 2, which will get me 84 meters squared. Okay, last thing in this section, the shadow problem. So this is actually going to feel a lot more similar to something we did at the beginning of the semester with proportions, but it's proportions involving triangles, and that's why it kind of comes out in this section. And this is a problem that if you're going on into higher levels of mathematics, teachers love these problems of shadow problems because it deals well with proportions, it deals well with right triangles, it deals well with rates and even derivatives when you get up there. So you're going to probably see this again. If you plan on going further in mathematics, I would make sure you feel pretty comfortable with this. Okay, so here's the problem. Let's say that I'm 6 feet tall and I'm casting a shadow that is 4 feet. And I'm near a building that is casting a shadow of 20 feet. So the question becomes, how tall is the building? So if we draw a picture and kind of fill out what information we have, we got my height, got my shadow length, got the building shadow length, and then I'm trying to find X. That's kind of my unknown. Now it seems like they're almost unrelated, and there's not really a good way to figure this out other than pulling out a really long measuring tape and climbing to the top of the building and dropping to the bottom. But that's not true. There's actually kind of a hidden shape here, and that hidden shape, surprise, surprise, is a triangle. So the sun is casting a shadow, and that like sun ray, that is kind of the tip of my shadow. That is going to be my hypotenuse of my right triangle. And so these are what we call similar triangles. And since these are similar triangles, what I can do is I can use them to build a proportion. So that proportion, there's a couple of ways you can write it. You can either write kind of the height of the building over the shadow length is equal to the height of the person over his shadow length. You could also kind of compare heights and shadow lengths. So you could do potentially x over 6, height over height, and then shadow over shadow. As long as you're setting it up in one of those two manners, you're going to get a correct answer. And the other nice thing is, if you're getting an answer that doesn't really make sense, you can see that at the end and then go back and kind of fix your proportion. So once I have this, I cross multiply, divide both sides by 4, I get x is equal to 30. And in the context of the problem, that would make sense. The shadow relative to my height, I'm taller than the length of my shadow, so the building should be taller than the length of their shadow. If you flip your proportion or set it up wrong, you're probably going to get a height that is smaller than 20, which doesn't make sense. So make sure you're kind of checking the context clues of the problem. And again, that's not a correct, well, it's very close to a correct answer. I'm just missing my units. And so if you want to be super on top of things, you would say the building is 30 feet tall, but at the bare minimum, I would like you to at least say x is equal to 30 feet to make sure you're including your unit.